All right, let's get right into it. Today, we're tackling a massive challenge in the world of AI, and we're going to look at a really clever solution for it called TurboQuant. The promise here is huge, shrinking AI models down, but without making the usual compromises. I mean, it's pretty obvious to anyone paying attention that AI models are getting shockingly powerful. They're already doing things like writing code, creating incredible art, and just making sense of enormous amounts of information.
But there's always a catch. All that incredible power comes at a pretty steep price. These models need a ridiculous amount of memory, which makes them slow, and it makes them incredibly expensive to run. It's become a real bottleneck for progress.
So here's the big question. What if you could have your cake and eat it too? What if it were possible to compress these giant models? I mean, slash their memory use by 75% and lose absolutely nothing in performance. It it sounds a little too good to be true, doesn't it? So let's pinpoint the problem. When you're having a conversation with a large language model, it's using something called a KV cache. Think of it as its short-term memory. And for search systems, you've got these vector databases that have to store just mountains of data. In both cases, memory is the thing that slows the whole operation down to a crawl. Well, the solution, or at least the idea behind it, is a concept called quantization. The best way to think about it is like a shrinking ray, but for data. The whole goal is to take these massive, complicated numbers that live inside an AI and just make them tiny. And this gets into the how. It's called vector quantization. You're essentially taking these super precise numbers with tons of decimal places, we call them floating point numbers, and you're converting them into really simple, small whole numbers, or integers. The analogy here is perfect, really. It's just like taking a beautiful, high-quality PNG image and squishing it down into a much smaller JPEG. You lose a little information, sure, but the trick is to not lose anything important. And here you can see exactly what that looks like. On the left, you've got the original data, these long, super precise numbers. And on the right, the quantized version. Those same values are now represented by just a couple of bits, like 11 or 01. You can see right away how much space you're going to save. But, and there's always a but, this is where things get tricky. When you shrink data like this, you're always running the risk of losing something important. And that creates this big dilemma around accuracy. So the first way we can measure this loss is something called mean squared error, or MSE. The easiest way to think about it is just comparing that compressed JPEG to the original PNG. MSE basically measures how different the individual pixels are. You want that number to be as low as humanly possible, right? You want to preserve that original quality. But then there's a second, much more subtle type of error. It's about preserving something called the inner product. And this isn't about just one piece of data changing. It's about making sure the relationships between all the pieces of data stay the same. Imagine a constellation of stars. You don't just care about keeping each star bright. You need the distances and the angles between them to stay exactly the same. That's what this is. And it's absolutely crucial for how AI understands things like similarity and context. And this right here is the problem that researchers have been banging their heads against for a while. Most of these compression methods, they're pretty good at minimizing one type of error, but they usually make the other one worse. So the billion-dollar question, can you actually solve for both? Can you get that pixel-perfect quality and keep the constellation perfectly intact? This is where TurboQuant enters the picture. And it does so with a trick that is so simple, it's almost funny. It all comes down to a random spin. The way it works is it's beautiful. First, it takes your data and it applies a random rotation. It's basically just spinning it around in this imaginary high-dimensional space. Now, here's the magic. That spin makes the data's coordinates suddenly become predictable. They start to follow a known statistical pattern. And because of that, you can now compress each little piece of data all by itself, as simply as possible, without having to worry about how it affects all the others. And hey, don't just take my word for it. The researchers themselves say it right here. This near independence that you get from the random spin, that's the secret sauce. It takes what was a really complex, interconnected mess and turns it into a bunch of simple, separate little problems. Okay, so this first version, which is called TurboQuant MS, is absolutely fantastic at minimizing that first kind of error, the mean squared error. But it turns out it creates a tiny, consistent error, what we call a bias, when it comes to preserving those all-important relationships, the inner products. So it's really close, but it's not quite perfect. So what did they do? They made a second version, TurboQuant Prod, to fix this. And it's so clever. It's a two-step process. First, it runs that original algorithm, but it holds back one big from its budget. Then, it looks at the tiny little error that's left over, and it uses that final bit to compress just the error itself. When you combine those two things, the bias completely vanishes. It's a really elegant fix.
So all this theory sounds great, right? But does it actually work in the real world? Well, let's take a look at the results. Check this out. This is the famous needle in a haystack test. You ask an AI to find one tiny, specific fact inside a huge document. On this chart, green means a perfect score. And as you can plainly see, TurboQuant gets it right every single time. It perfectly matches the original uncompressed model, all while using 4 times less memory. That's just an incredible result. And here's the visual proof of why it works so well. On the left, you're looking at the error for that second improved version, TurboQuant Prod. It's a perfect bell curve, and it centers exactly on 0. That means no bias. Now look at the right. That's the simpler first version. See how the whole curve is shifted just a tiny bit to the right? That's the bias. And that second algorithm completely gets rid of it. And there's another huge advantage here. TurboQuant is what engineers call an online or data-oblivious algorithm. What that means in plain English is that it doesn't need to spend a ton of time studying a data set before it can work. It can just start compressing data on the fly instantly. And that is absolutely essential for any kind of real-time application. Okay, let's look at the cold, hard numbers. The original model, full precision, uses 16 bits of memory, and it gets a performance score of 50.06. Now just look down at the bottom row. TurboQuant, using only 3.5 bits, that's a compression of more than 4.5 times, gets the exact same score, 50.06. It literally matches the original performance while using just a fraction of the memory. And what does less memory get you? Speed. A lot more speed. Because there's so much less data to move around, TurboQuant can potentially speed up some core AI calculations by up to 14 times. I mean, that's a total game changer. That's the kind of thing that could unlock real-time AI on the phone in your pocket, not just in some giant data center. And get this. This isn't just some lucky hack that happens to work well. This algorithm is mathematically proven to be almost perfect. Its performance is within a tiny margin of the absolute theoretical limit, the best any compression algorithm could ever possibly do. It's not just good, it's pushing the very edge of what's even possible. So all of this leaves us with a really fascinating question to think about. We've just seen a method that can take AI's biggest problem, its massive memory use, and shrink it dramatically with no loss in quality. So if we can make powerful AI small enough to run on our phones, fast enough for instant answers, and cheap enough for everyone to use, what kind of world is that going to unlock?